So I don't know how many of you know about this program, about the exchange program with Perimeter. We'll have lots of information in the afternoon. So the idea in the morning is just to get started. So there'll be, of course, an exam in the weekend, and the exam will be based mostly on the lectures. So there's also a question period. So we're asking all the speakers to stop after 1 hour, and then there'll be 15 minutes for questions. So you can ask short questions during the lecture, but save the longer, more conceptual questions for the 15-minute period. And then we'll force them to stop. So, so are there any problems, immediate problems? So of course we have secretaries and everybody who can help you with that. But if there are any urgent problems, just raise your hand and we'll try to take care of it. Okay, very good. So we'll start the first lecture with Pedro.
Very good. So welcome everyone. So I'll be talking about anti-de Sitter spacetime. So I prepared some lecture notes. Did everyone see that they exist? Is everyone aware of the existence of the lecture notes? Very good. So the lecture notes are basically a set of problems. So there is some explanations, but most of it is problems. So there are 52 problems there. And so basically the idea is that you should go through the problems, and in going through the problems you will learn about this remarkable spacetime. And in the lectures what I'll do is probably basically end up solving some of these problems while explaining. Some of them I will not explain. And if there are problems that you really struggle to do, just ask them and I will solve them during the class. But basically, I prepared this note so that you could really get familiar with the concepts by solving these problems in the notes. Okay, very good. So let me tell you just some overview of what we are going to see about this spacetime that's called anti-de Sitter. And by the end of the lectures, you will know 3 things about anti-de Sitter. That are 3 remarkable aspects of anti-de Sitter. You can understand anti-de Sitter from many points of view, but there are 3 properties of this very important spacetime that we will see in great detail. In lecture 2, we will see that this spacetime is very symmetrical. It's as symmetrical basically as flat space. Empty space has a lot of symmetry, right? We can translate in time, do boosts. We have lots of symmetries. This spacetime, like a sphere, is also very symmetrical, right? So there are a bunch of spacetimes that we should all know, because if we want to learn about curved spacetimes and general relativity, we better know the simplest and most symmetric spacetimes. And they are basically flat spacetimes that we know since we are born, spheres that we know since kindergarten, and ADS that you will now also know. So spheres, ADS, and flat space are roughly all as symmetric as they can get. Another very important thing is that anti-de Sitter space is a box. It's a gravitational box. And in physics, it's very important to have boxes, right? So you often need to put your system in finite volume, study it. It's very good to have a controlled box that you can put things on. Now, if you think a bit what exactly is a box is something that you put inside, and then there are walls. Things don't get out. So it's the same in ADS. If you are an observer in ADS, you stand in ADS, you throw something to the left, and a little bit after that, something comes back. So in that sense, it's a box. It's a very special box, a very beautiful box. It's a box that has no center. Everyone inside this box is the same. So it doesn't matter. It's a box where you are, here you are, you throw this piece of chalk to the left, it comes back after 2 hours. Someone else is in ADS, throws another thing to the right, comes back in 2 hours. It's isotropic. In any direction that you throw the piece of chalk, it comes back in 2 hours. It always comes back in 2 hours, depending on the size of anti-de Sitter. It always comes back in a fixed size. So it's a very symmetric box. It looks like a bit like an harmonic oscillator. If you are in an harmonic oscillator and you have something swinging, it has a frequency, right? And it's always the same frequency. But not all points are the same. That's true if you are in the center, right? If you move, you would feel differently if you are in different points of the line. Here it's a bit like every point is like an harmonic oscillator, every point of the box. It's a very special gravitational box. It's also very hard to put boxes in GR, because you cannot just put a wall. A wall will back react on space-time. You would have to decide where is the wall. exactly, but that's very hard to define. So it's a beautiful gravitational box. And the other thing that that we can think of it is as a way of thinking. You can think of ADS as copies of flat space-time. And these copies, you can think that they encode physics at different energy scale. It's a bit like, imagine you have space-time, a copy of flat space-time if you want at big distances, and then another copy if you want shorter distances, another copy if you want shorter distance still. And this space-time can be seen as stacking copies of flat space, each copy describing physics at different scales. So 3 different ways of thinking about this space. One, as a very symmetric object, we will draw pictures like hyperboloids. One of ADS as a box, we will draw cylinders and say there is a box, the bound like a wine box where you put a bottle of wine. And copies of flat space, we will draw flat space as a plane that's flat, and then we will draw copies that become smaller and smaller, and we would say that ADS could also be thought as this kind of space-time where we put together these copies of flat space. And these 3 descriptions, they are the same. They are equivalent, and we are going to explain how they are equivalent in the same way that you can describe a sphere in many ways. You can draw a sphere, you can draw a map and say how scales are on the map, and there are different ways of understanding a sphere, different coordinates that describe the same thing. An observer feels the same thing, but different descriptions can be useful for different things, right? So it's very useful to have a map. It's sometimes very useful to have a globe to visualize things, and depending on what you are going to do, you will want to choose one description or the other. So today, this would be lecture 2, this would be lecture 3, this would be lecture 4. In lecture 1, we will do something related to spheres and background, just to make sure that we are on the same page and we have the relevant math for understanding, and it will be very closely connected to these very symmetric spaces because, as I said, ADS and spheres differ just a little bit, a tiny bit, and they are both equally very symmetrical. So the main motivation for studying this space-time for me is twofold. Is on the one hand, it's a box, and I think it's super important to have boxes. So for me, the second one plays a particularly important role. But the second one is that it shows up in a huge area of theoretical physics within string theory in what is known as the ADS-CFT correspondence, which is a correspondence between theories of quantum gravity inside this box and theories that live at the boundary of the box. We are not going to describe ADS-CFT, except for a few words at the end of the last lecture that I'll give you a flavor of what it is. We are going to describe the box and the arena as a space-time. But if one day you wanted to go and learn about high-energy physics and string theory, as I said, it occupies roughly, I would say, a finite fraction, maybe a third or a half of the research in string theory is somehow related to ADS-CFT related aspects. It's a very big chunk of the research that we do. Okay, so any question about the general topic of the lectures? Otherwise, yes? You can, if you can take pictures. It's recorded, but you can take pictures. But everything is recorded and you have the notes. Yeah, but sure, yeah, you can take pictures. Any other question? Okay. Very good. So there are 2 things that I wanted to make sure that we know today. What is a metric and what are geodesics? So does everyone know what a metric is? Can you raise your hand if you have never worked with metrics? Oh, everyone has. Really? I'm surprised. I thought some of you did not have GR. So how many of you have written a metric for a sphere? Okay, not a sphere, but have written a metric. Some metric. Okay, almost everyone. Okay, very good. So we'll go fast in this first lecture, and we'll have more time for questions. That's fine. Okay. So So let me start with the definition of a d-dimensional sphere. And as I said, there are many definitions, but here is one. We can think of a sphere by saying it's a set of points in a higher dimensional space, so d plus 1. Okay? So we put a two-sphere in 3 dimensions, such that their distance to the origin is fixed. Right? So of course, this is the definition of a sphere. And in this definition of the sphere, so we have this, this sphere, we have the radius of the sphere, r, and then we could describe this sphere like this. Now, one thing we want is to trivialize the sphere and to introduce coordinates to trivialize the sphere constraint and introduce spherical coordinates like some theta, then it would project here, and some theta, and so on, some theta 1, theta 2, and so on, such that this constraint would be automatic, and we would get a manifestly d-dimensional space instead of a d plus 1 dimensional space with a constraint that puts it in d dimensions. Then we would write something like x1 equal r cosine of theta 1, x2 equal r sine of theta 1 cosine of theta 2. So you see that if it was not for the cosine of theta 2, the square of this plus the square of this is r squared. Now we put x3, we write r sine of theta 1 sine of theta 2. Now you see it works. The sum of them is all the same, but you put now a cosine of theta 3, and so on, until the very last one, the x d plus 1, where you put here sine of theta 3. Okay? And so it's obvious, right, that if you sum the squares of all of them, not theta 3, sorry, sine of theta d, that if you sum the square of all of them, that it's r squared. And now we can say that the sphere SD is just the set of these angles theta I, where what is the range of this theta? You see that theta 1, it's enough to cover from 0 to pi. So we would say theta 1 belongs from 0 to pi, whereas the other ones, theta j, you see that theta 2, I go around 2 pi, and you can check that everyone else lives from 0 to 2 pi. Okay? And a sphere would also be defined by these coordinates or these coordinates. But coordinates by themselves are not very important. What's important is to have a notion of a distance between points. Right? So if you have coordinates, you say I have a point at some position, x1, x2, x3, x4, whatever, some labels. Or I have a point at some angles, theta 1, theta 2, theta 3, etc. Then I have a neighboring point at some other coordinates. That's not physical by itself. What's physical is to say, what's the distance between these points? If I throw geodesics, do they open up or do they contract, and so on. That's what's physical, right? Not the labels of the points themselves. So, so it's very important to introduce this notion of metrics to measure the distance between the points. So a metric, when you have, so this would be some infinitesimal distance between 2 points. And this we define by saying if I have a bunch of coordinates, let me call it dzi, dzj, the object that contracts with this quadratic form would be the metric gij that would depend on the z's. Right? So the simplest example would be flat space, where if I have flat space and if I have 2 neighboring points, the distance ds between them, if I know the variation dx1, if I know dx2, and if I know dx3, I just use Pythagoras theorem, and I would write that ds squared is just dx1 squared plus dx2 squared plus etc. plus dxd. Or let's say it's flat space in d plus 1 dimensional square. So this would be flat space R d plus 1 dimensional, like the metric where we put the sphere. So this tells me how points that are separated by a little bit, how they are, what's the distance between them. Any question here? So far everything is familiar, right? Now, one thing we can do once we have this metric is consider not only infinitesimal distance, but we can consider some finite distance. So for example, we could imagine, say we have in 3 dimensions and we have some cube. And suppose I want to study this distance from this point to this point. And I want to ask what's this distance d here. So what would you do to compute this distance d? Right. You would say this distance, you would say it's the integral of, and now you will say that x1 will be x1 of time, x2 will be x2 of time, and x3 will be x3 of time. And then, what would you do? You would say, I integrate the line element, ds, from point A to point B. This would be A, this would be B. In other words, you integrate in this parameter t from the first time ta to tb, square root, ds is that, of the derivative of x1 square plus x2 square plus x3 square. And this is what this type of metric here with square root of gij, more generally it would be z dot zj, if I am in any space-time. This we would call the Lagrangian, and I called it in the notes Nambu-Goto Lagrangian. And so this functional computes infinitesimally the distance between points. We integrate between 2 points, for example, parametrizing the points like this, and we get the length. Now, very important to note that this Lagrangian doesn't care how I choose to parameterize these points. It's physical, right? It's the down length between these 2 points. So it doesn't matter how I parameterize it. You see that if you change t to f of t, each derivative picks f prime of t squared, right? Gets out of the square root as an f prime that is precisely cancelled from the transformation of the integration variable. So if you use t, and if someone uses t squared, you will get the same result. So for example, for that curve there, we would say, this would be an example. We would say, for example, this could be just t. This, when t goes from 0 to 1, so let's suppose this is 1. It's a unit cube. When it goes from 0 to 1, this would do the job of parametrizing a line that goes from 0, 0, 0 to 1, 1, 1. But if you put here t squared, t squared, t squared, it also does the job. And the result is the same. It doesn't matter. You pick whatever you want, right? So for example, and let's put here, could be t squared. T squared would also do the job of going from 0 to 1. It would describe the same curve. And then what would we get if we put this? We would get the integral from 0 to 1 dt square root of 1 plus 1 plus 1, which is square root of 3. Okay, and that's, of course, the result for the length of the geodesic of the unit disk, of the unit cube. Okay? Again, if you don't believe me, you can check that if you put t square, that you would get the same result. Okay, so this would be a metric, a trivial metric in flat space. What would be the metric for the sphere? How do I compute the metric for the sphere? Well, one thing you could do, and you should do once in your life, is draw a small ds and graphically understand what is this small distance in terms of θ1 and θ2, and just use trigonometry and write ds squared using Pythagoras and write down the metric directly. Right? So that would be a way to do it. You would just go here and just geometrically immediately write down what it is. When you change a little bit of θ1, a little bit of θ2, what is that length element? Right? In practice, we never do like this. Okay? But we should do it once, but that's not in practice what you do. What do? Is you say that I have the metric in flat space, I have the distance in flat space, and this distance here, I can just plug this parameterization into the metric in flat space. I compute the various differentials. So for example, a small dx2 would be something like r cosine θ1 cosine θ2 d θ1 when I vary θ1 minus r sine θ1 sine θ2 d θ2 when I vary θ2. And I plug dx2 like this inside the metric, dx1, dx3, and so on, up to dx d plus 1, and I see what is the resulting distance. Is it clear to everyone? That's much faster to do. Just do some algebra, you plug it into Mathematica, and you would get that the metric would be the distance square. It comes with r squared in front, of course. And then, let me not get all the cosines and sines mixed up. And then the metric in spherical coordinates in oh, okay, I don't have it here. Okay, so it would be something, I guess I will have to do the exercise. So dx1, dx2, so it would be something like d θ1 square plus sine square of θ1 d θ2 square plus sine square of θ1 sine square of θ2 d θ3 square, and so on. Okay? And this would give you the metric of the sphere. This would be ds squared for the sphere in d plus 1 dimensions. Another way you could say is that ds squared for the sphere is just equal to the flat metric dx dot dx, where this x is a d plus 1 dimensional vector, with the constraint that x squared is equal to 1. Now, in practice, what does it mean? It means that you can either solve this constraint, for example, using that, or using any other way of solving this constraint, right? You could, for example, solve this constraint by saying that x d plus 1 is equal to the square root of r squared minus the other ones. Now, of course, this one would not be so good because it's not really the square root. There would be plus or minus, and I would have two patches, the two patches of the sphere. And that's fine. Then I would get the metric. It would be some metric here. If I do this, it would be some metric dxa, dxb with some metric gab, where now this a and b would run only from 1 to d, and they would parameterize the base of the sphere, right? So it would be like parameterizing this height x3 in terms of the bases x1 and x2. You would just say where you are, and you would get the point x3. And again, how would you compute this metric? you just compute the differential for dx d plus 1. You take the derivative with respect to x1, derivative with respect to x2, and so on. You compute this differential. And then you plug the square of this differential here plus the other ones, and you get the metric in these coordinates. All clear? Very good. So there's one last set of coordinates for the sphere, one last set of variables I would like to describe for the sphere, which are stereographic coordinates. So another nice set of coordinates, another nice description of the sphere. Is given by imagining that if I have a sphere, if I take the North Pole, and I have any point of the sphere, if I imagine a line that passes, that goes from the North Pole to that point and continues, it will intersect this plane at x d plus 1 equals 0 at some point here. Right? And so parametrizing this point here, let's call it u, is the same way each u gives me a point p. Do you agree? So can someone tell me what is the South Pole? The South Pole, this p, what point u would it correspond to? 0, right? So if I take this point P, it would be here, u equals 0. What about the North Pole? Infinity, right? I take a tangent there. It was very far away, right? So the further and further. So this would be at u equal infinity. And so in these variables, you would cover the full sphere with these variables u. These variables u, they are in d dimensions, not d plus 1, just like the sphere, right? And in these variables, you can see that the metric ds square would be something like du dot du over something like this. It should be like this. Where, one second. Yes? So these coordinates, u, I call them stereographic coordinates. Yeah, just a name. And they are defined. Let me write the explicit definition. If you want to check, you can see that x would be given by 2r u over r squared plus u squared. And the last component would be r squared minus u squared over r plus u squared. So you see this is the last component, this x d plus 1 component of x. And this would be the first d-dimensional components. And you can see easily, this is one of the problems, that this indeed is a point on the sphere. And you can also easily see that defined like this, u as this geometrical meaning as being the point where it intersects the plane. Now again, how would you compute this metric? Trivial thing, you just take this, you compute dx equal ta ta ta, and then you just write dx squared. Right? Just that. How should you do it at least once? As I said before, I think it's nice to do it geometrically, to practice a little bit. You take a point here, and ask if I have a neighboring point here, that means 2 neighboring points here. These are the labels of the points, U1 and U2. This is the physical distance between them. This is what is really the distance, ds square. Given 2 points here, you can project them there and see what this distance is. And you should do it geometrically. Of course, you should do it in a smart way. You should say, these points are aligned under the axis x1, and all other x's are 0, right? You don't lose anything in doing that. Then the metric becomes just, you can put all the other ones to 0, and you get just dx1 square over r square plus u1 square. And you should just understand that when you do it, that indeed, if I take 2 points here, then it's just a circle. That if I have 2 points separated by du, you should just compute this stuff ds, and you want to check that geometrically this ds is just 4 r to the 4 du square over r squared plus u squared squared. Now without vectors, because we align things in a clever axis. This is the axis u. Oops, I did a mistake here, right? So this line should be here. Right? It's this intersection with right? It's the middle of the sphere, right? It's xt equals 0. So I drew it down here. Okay. Now it's correct. So you should just check that 2 points here du map to a distance ds according to this formula. That ds, this ds is equal to this. So you can just see it geometrically. You should do it once. But in practice, we never do this. When we play with GR, it's always the same story. Plug some parameterization into the differential, plug it in mathematics, and get the result. And that's, in practice, how you would do. OK, or do it algebraically. But it's very useful when practicing with these distances to do a little bit of this. OK, so we have gone through a bunch of the first 10 problems that are in the notes. This is a bit trivial, and so on. So for example, an interesting exercise is to, for example, taking that Lagrangian, let's maybe just do this exercise just to practice a little bit. Let's suppose, just to get some experience with this Nambu-Goto Lagrangian, I want to compute the length of this curve that starts from the North Pole and goes to the equator. So this curve here, let me make a comment. So first, the length of the curve is, of course, equal to 2 pi r over 4, right? It's just 1/4 of a full length of a circle that goes around the circle. And the second comment is that this curve is a geodesic. And geodesic means it's, in this case, a curve of minimal, but what's important is that it's extremal length between these points A and B. Right? Do you agree? So let's just get some experience. Let's just try to recover this distance. So this length from A to B, what would it be? So here, you see, you can say that this length, very conveniently, just changes this angle θ1, and the other angles θ can all be fixed. I can fix them all to whatever I want, right? So I could go here and say that this stuff here is irrelevant. So my distance, ds, is just r d θ, and the integral will be just this integral. And I integrate from 0 to pi over 2, so I get r times pi over 2. Do you agree? So just very easy to go from the metric and get that. Now, let's do that computation in stereographic coordinates, just to see that, of course, it doesn't matter where we do it. So let's try to compute the length of this circle here. Right? So what would this length be? Where do I integrate this from in stereographic coordinates? What integral should I do? So you see that here I can say that u1 is equal to u. All other ui I can set to 0. Right? Everything is in one direction. Then my metric ds square would be what I wrote here. My element is this. And so this, I can take the square root. So it's 2r du divided by r square plus u square. And what should I integrate this from? So I should now do the integral. 2r du over r square plus u square. From what? What are the integration limits now? From infinity, right? So as we go from infinity all the way to r, right? So we could say I integrate this from r to infinity, and this is pi over 2 times r. Is it obvious? It's true. It must be true. You can check it. But let me just see the dimensions are correct, because they don't look correct, because here I forgot the square. So if I rescale u by r comes out right away, right? So it becomes r times the integral from 1 to infinity to dy over y squared plus 1. And this integral must give pi over 2. Okay, it's just a fact of life, for sure. Must. Okay? It's actually a bit funny. Doesn't look obvious to me, but okay, it's true. Okay. That's because we are to use the mathematics, but it's just a true statement. Very good. So that's most of that's the most important things. So now so that was just to make sure we are on the same page with respect to metrics. So what we have checked up to now is that we have spheres. Spheres, now we can think of them as a bunch of definitions. So we can say it's x inside rd plus 1 plus a constraint, x squared equal to 1. We could say it's the base x1 up to xd, and then the last one would be plus minus some square root. This would be parameterizing the base and having two patches. That's an equally good definition of the sphere. We could say it's a set of angles theta I, or we could say it's a set of stereographic coordinates u1 up to ud. And these last three descriptions make manifest that a sphere is a d-dimensional object. The first one embeds it into d plus 1 dimensional objects, which is fine. We can do it. We should always have in mind that the sphere is just a d-dimensional object, right? We don't have the right to ask, what happens when I'm on the sphere when I go inside? That doesn't exist. The sphere, the inside doesn't exist, right? In the same way that if you explain to someone the Big Bang and you say the universe is growing, it's like a big sphere, and everyone asks what's inside and so on, it doesn't make sense. It's just, the sphere is the sphere. It's just the surface of the sphere, right? Okay. Then, with this space, whatever definition we use, we have this, the idea that there is a metric, ds squared on SD, that tells us how points on the sphere, what's the distance between neighboring points. And then we have the important notion of length between points A and B. That is a function of a path, gamma. This path we get by parameterizing coordinates zi as a function of t, but it doesn't matter what the parameter is. And this is just the integral of square root of this metric giz z dot I z dot j dt. Okay, and this was probably just review for everyone. This was just to set up the notation. Is it true that everyone is more or less very at ease with this concept here? Is it true? Okay, now the next step I want to review a little bit is that when we have this notion of length, a very useful concept is the idea of trying to extremize this and studying geodesics. To ask, I don't care about any length, I care about lengths that extremize, that are the extrema between points A and B. For example, in the sphere, geodesics are arcs of equators. An equator is a geodesic, and a tilted equator is also a geodesic, right? So geodesics, this extrema of the length, are very important constants. So these are the curves gamma such that this length is extremum. Is an extremum. It could be a maxima, it could be a minima, it could be a saddle point, but it needs to be an extrema. Okay, so is everyone familiar with the study of geodesics, given a metric, how we would study geodesics on the space-time, how the particles move along geodesics, as you know? Right? So if I throw a particle in empty space, it continues along a straight line. If we throw a particle in a black hole, it follows whatever geodesic it tells it to go when the space-time is curved. So it's very useful to know about geodesics. And does everyone know how to describe geodesics? Is everyone familiar with given a metric? Now we have many metrics in many coordinates. How would I go about describing geodesics? Who is not familiar, who has not played much with geodesics? Okay, so a few people now. Okay. Okay, so I think maybe now some of the things will start becoming a little bit more interesting for most of you. Let me just make one last comment, which is that this metric here, you see, du dot du, this here would be the metric of flat space-time, which would be to say that this plane here, I could define a metric on this u-plane that would be flat. Now, the metric of the sphere is not the metric of flat space-time. It's the metric of flat space-time times some function, right? That's not the same as the metric of space-time. However, it is true, as we see in this example, that the metric of the d-dimensional sphere, it's not equal to the metric of d-dimensional space-time, but they are proportional to each other. Right? That's true. Right? The sphere is not the same as flat space-time, but they are conformal to each other. So we say that SD is conformally flat. And what it means is that if I have flat space-time, if we measure distances in flat space, in the sphere, if I want to think of that flat space-time as a sphere, I have to rescale the distances by this factor. See, for example, when u goes to infinity, as du dot du is rescaled by a factor that makes it very small. That's because infinity, I don't want distances at infinity to be very big. Infinity is just a point on the sphere. So this fact that this is going to 0 when u goes to infinity is telling me that infinity is not really infinity. It's just another point. I become u, bigger, 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 and the distances become smaller and smaller and smaller, even though I'm going to very large u's. Right? So if I consider a big arc here at u equal infinity, that's a very small distance. Because a big arc in this plane, when u goes to infinity, a huge arc here in the u plane, is describing in the sphere some very tiny arc close to the North Pole. Right? The further you go to the future, the smaller the arc is, and the closer you are to the North Pole with a smaller and smaller arc, if you take this arc and make it go to infinity. So these distances are rescaled. Okay? But it's true that if I have a flat space-time and I rescale the distance, I have the same thing as the sphere. Now, sometimes in physics, you can have a theory that is invariant under rescaling. For example, you might have seen pictures of phase transitions. In a phase transition, you have a fractal structure and you don't know at which scale you are. Things are scale invariant. You have in a phase transition, for example, say in some kind of liquid gas phase transition, you could have parts of liquid that are black, parts of gas that are white, and you see many black, many white, and you see a big blob of black, a big blob of white, and some many small blobs, and you zoom in, and what you see when you zoom in, the same story. Some big, some small, and you zoom in, and what you see, some big, some small. You cannot tell at which scale you are when you have a phase transition. Why? Because all scales are important. The correlation lengths diverge, and now you don't have any typical lengths, and all lengths are important, and you have physics happening at all scales. Okay, so this is something that happens in physics, one sec, is that sometimes you have these phase transitions where correlation lengths blow up, and physics at all scales is important. Like I said, liquid-gas phase transition. In magnetism, when you go to the phase transition and you have spins up and spins down in different regions, and again, you have some scale invariance. Now, that means that if I have a piece of rock, a piece of material, and if I just give me a picture, I don't know the scale. I don't know if it's 1 centimeter, if it's 1 millimeter. I can rescale things, and things will be the same. Now, you can imagine that if you have a big rock, like the size of this room, you could rescale things here, and rescale things here in the opposite direction, and no one will notice. Provided these things are not very small, if you can imagine that if you could rescale everything up and down, maybe you could also do it locally. You see, you could here zoom out a little bit, now go here and zoom in a little bit, go there and keep it, go here and zoom out. And this would be the idea that perhaps in these theories where you have no scale, maybe you have no scale locally. That you have the right, in a piece of rock here, a macroscopic piece, you zoom out. A macroscopic piece there, you zoom in. In those theories that have no scale, if you have the right of do these local transformations, then physics in flat space would be the same as physics on a sphere. Why? Because what are we doing here? We are saying that distances on the sphere are equal to distances in flat space, but at each point of the flat space, I rescale by a different amount. Okay? So in that sense, living in flat space or living on the sphere would be the same. Those theories that have no scale, flat space or the sphere would be equivalent. Right? So for those theories, people that would say the Earth is flat, they would be right. It's okay. You could not argue with them. It's, fine, okay. For me, it's round. For you, it's flat. Doesn't matter. It's the same. Physics would be the same. Now, here, of course, if you are two observers, there is a length scale, which is the radius, and you would know that this distance you compute with this formula. Okay? Okay, and so theories that are scale invariant, this notion of conformal invariant is very useful. That space-times, if one is proportional to the other, that means they are not the same, except if there is no scale where I can rescale things arbitrarily locally, and then the physics on this space-time and this space-time should be related to each other. One last comment I want to make is that imagine I am in a small region, and the metric in that small region, U here, I am in a small region here, so that I'm exploring a small region here. Then in this small region, U is approximately equal to some U star. And therefore, the metric here, to first approximation, is approximately equal to some function of u star, that's a constant, times the metric of flat space. Okay? And that is always true. It is just a statement that if I'm in a small enough region, it looks flat. Right? The Earth looks flat. Right? So here, of course, it looks flat. Everything, if it's a small region, it looks flat. Okay? That's true in any space-time that you write. If you zoom in close to a point, it looks flat. And indeed, physics looks flat when you are at small distances. And that's the equivalence principle. It's the statement that things locally, they behave effectively like flat space. Okay? Good. Okay, on to geodesics then. So we have the length of a curve that we saw is the integral from point A to B of the infinitesimal length, or if I parameterize the points, it will be, there is some parameter t, square root of gij of some coordinates zk of t, derivative with respect to t of zi of t, derivative with respect to j of zj of t. Right? And like I emphasized before, in this language, whatever parameterization you use, you pick some curve, zi of t, but it's the same, it's equivalent to picking some other curve, zi of some function f of t. That's equivalent, and everything is invariant under this choice. And then what we want is to find geodesics where this length is extremum. And so this would be our Lagrangian that depends on variables and velocities, positions and velocities. And this extremum of the Lagrangian is given by the Euler-Lagrange equations, which would be that the derivative of the Lagrangian with respect to zi would be equal to the derivative of the Lagrangian with respect with the dot. Okay, so everyone is familiar with this? Yeah? So if not, you can Google a little bit. So this would give you, if you do a variation of this Lagrangian, you are careful with changing delta z, you can vary this guy, you can vary this guy. Any Lagrangian that you have, this condition extremizes this Lagrangian. Now, these equations of motion that you get from this Lagrangian, they are messy because of the square root. Taking derivatives of a square root is a nightmare. You get 1/2, a square root downstairs. You have to take derivative of what's inside. They are ugly equations. Okay? Now, they are messy because of square root, but we can take advantage of the fact that we can pick f of t as we wish. And doing that, we can simplify and get very nice equations. Okay? More precisely, when you take derivatives of square root, you get 1 over square root. And so a nice f of t to choose is to choose an f of t where this square root is equal to 1. Right? That's a very physical choice. It means that the velocity is just equal to 1. In other words, that's choosing t to be just equal to s, t to measure the length along the curve. If t is the measure of the length, then for me, that I'm a local observer, the velocity is just t, 0, 0, 0, 0, 0, and the velocity is just 1. Right? Or, in other words, if this square root is equal to 1, then S is equal to T. Right? So it's just a choice. You choose T so that T is just the proper length along the curve. Okay? So this choice of condition where T is S, and therefore the velocity is 1, we can write more precisely 1 is equal to the inside of the square root. So 1 is equal to Gij of this Zk, Z dot I, Z dot J. This is a choice. Right? So this is the same as velocity equal to 1. In other words, the time that we measure T is equal to the length, is directly measuring the length. As I'm evolving, I'm measuring the length locally. It simplifies the equations dramatically. And in this case, the equations become the following. X double dot I minus Christoffel KL X dot K X dot L equal to 0. Okay. Where these Christoffel symbols, gamma I, KL, are obtained by some metric and some derivatives of metric that are written in the notes and that we are never going to use, so I'm not going to write it down here. And then, let me go through, it's a bit long, this logic, but now we will recap in a second. And then you ask if I can write another Lagrangian, which is not this Lagrangian that before we called the Nambu-Goto Lagrangian. By the way, I'm using words for Lagrangian, but it's an action, but I'm assuming there's no confusion. I mean, Lagrangian normally is what's inside, right? This will be the Lagrangian, this will be the action, but we could ask if there is another Lagrangian that I use P for Polyakov, from what these equations of motion would follow directly without a square root. And indeed there is, and it's very simple. It's just the same Lagrangian without the square root. Maybe with some factor of 1/2. And this Lagrangian, if you vary its equations of motion, you get exactly to this box. So again, the statement is, we have this Lagrangian, but we have to keep in mind that we need to use this condition here. And so we can use this much simpler Lagrangian, called the Polyakov Lagrangian, with the condition that the velocity is equal to 1. Or we could use the Nambu-Goto Lagrangian, and these two Lagrangians are equivalent. The logic here was was not very clean, was derive the equations of motion, simplify them picking your parameter to be the proper length, get some very simple equations, and see that those very simple equations are the equations of motion from some much simpler action. Okay? Yes? Yeah, probably, yeah. Yeah. Thank you. More questions? Sorry? No, not yet. Sorry? Yes? Right, they will be, but at this moment, let's ignore ADS. There's no ADS, it's just spheres. But yes, we will see that when I say it's ADS will be very many copies of flat space, it's a little bit like here, like a sphere, but it's not exactly the same. It's a bit different. No, we should not make that analogy yet. So this Lagrangian is such that these are the equations of motion for this Lagrangian. So I write this, and now if I use Euler-Lagrange equations, I get this equation directly. So you see, I start from Nambu-Goto, I pick a gauge, I pick a parameterization I get here, and then I ask, how could I go directly from another action that lands here directly? And the answer is, there is no square root, and it's just much simpler Polyakov action, with the condition that the velocity is equal to 1. Yes? That's right. Good question. That's probably a simple answer to that. Let me think. Is there a simple way to know if I have two spacetimes, if they are conformal to each other? Is there? Let's see. Probably there are some curvature invariants, but it's very hard. In general, I have to think. Let me think about it. It's a good question. I don't know. So yeah. Okay. So like I said, all this is in the problems to do this algebra. The thing I wanted to do is to relate directly this Polyakov Lagrangian to this Nambu-Goto through a different procedure that is not this one here. This one here is what's explained in the notes and what you are encouraged to go through in the exercises. But you could ask, instead of starting with Nambu-Goto, fixing a gauge, getting some simple equations, and then getting a Lagrangian that gets there, can I do some funny manipulations to go directly from this square root and understand how to remove it and go here directly? And if you are curious about it, you can come and ask me. Otherwise, we stay with the derivation that I explained now. That's the derivation in the notes. So, as I said, today was just to set up the notation. So you should be comfortable with, given a space, there are many equivalent parameterizations that highlight different aspects of the space. In one parameterization, we could see it's flat. In one parameterization, we could see it's very symmetric, right? You rotate the points, and this condition is invariant. In other parameterization, we could have the angles, and we could very conveniently parameterize it on a plane. Then, once you have a given space, you can compute lengths along curves. It's a well-defined concept that just cares about the curve, not about the way you parameterize the curve. And from that, you can write immediately when you have a metric, you can forget about everything here and write immediately this Polyakov metric. This is the most useful one. You put a metric here, and now you write the equations of motion right away from this. You write the equations of motion just taking variations. You get some equations that are very simple, right? You just take the derivative with respect to z dot, dd time with respect to z dot, and you get some equations of motion. And if you want now to know, to compare with this box, you would use that to read off the Christoffel symbols. So that would be, in fact, the most useful and the fastest way to compute these Christoffel symbols if you wanted to compute them. Would be write down this action, compute its equation of motion, compare with this equation, and read them off. Okay? So that would be, in practice, the way you would go about computing these Christoffel symbols. And that's why I didn't even bother writing down the precise definition, because this would be a much faster way to compute them. Okay? And in this way, we would compute geodesics in this space. Okay? So I hope everyone is familiar with this, and that if you are not, if you found any of these points hard, go back to the notes, solve the problems, and try to search a little bit for Euler-Lagrange, geodesics. But these are the concepts that we will need throughout the lectures. Okay, we can move to questions now.
Questions? So wait for the mic so that, or else you can repeat the question.
Thank you. In the case that we say that SD is conformally flat, we could say that a region of SD is isomorphic to the space flat, maybe? I don't know if we could use that term in this case.
In the sense that you can label the points by points in flat space?
Yeah,
That's true.
Okay.
That's what a map does, right?
Exactly, yeah, that
A map
two topological
is
spaces, maybe? Okay.
A map, you just have points there, and to each set of points, there is a point on the sphere. So it's just a map between the two, and vice versa, right? They have an inverse. Given a point on the sphere, you can get a point of the map. Given a point on the map, you get a point on the sphere.
Thank you.
As you said, there are two different Lagrangians that give rise to the same equations of motion.
Yes.
In that case, the geodesic equations. What I would like to know is, well, obviously, if there are two ways, one would ask if there are more ways. So is there a general property of these functions that lead to the geodesic equations? I mean,
so
are there
like
more
I
choices?
said, the geodesic equations you can write as the Euler-Lagrange equations following from this action, for example.
Yes.
Okay, first of all, the proper equation is this one. It's just saying it's the extremum of this functional. Right? The rest is details. It's how you compute it with coordinates, how you choose to compute it. But this is the key equation. Right? Then the second, I would say, is the one that I start with the square root and I vary it and I get this equation, messy as it might be, that's messy, that's fine. Now this equation has a freedom that in this equation you can take advantage that you can pick your time, and if someone gives you a time, you can rescale it by making it something else. You could make, for example, this velocity not equal to 1, but equal to some function of time, if you like. Doesn't matter, as long as it's monotonic or something, it's okay. And you have the freedom. If you pick this choice, which is a very natural, very physical choice, because then it tells you that the parameter along my curve is the length of the curve, not only you get two nice things. One, the parameter is very physical. As I go along, I measure the length. That's great. And the equation simplifies a lot, and it becomes just this. So that's great. Moreover, this equation follows from a much simpler Polyakov action, which is quadratic action, no square roots. It's of the type that is like harmonic oscillator, something quadratic. It's trivial to derive equations of motion and to extremize. So it's only advantages. So this Polyakov, for us, it has no disadvantage, and it's just better. And so we are just going to use this Polyakov action, and we are going to forget completely about this Nambu-Goto in what follows.
Okay, thank you.
So we saw that the both Lagrangians give rise to the same equation of motion. Is there some information that is in the Nambu-Goto Lagrangian, but it's not on the Polyakov one?
There is this nice, so this Lagrangian, it had this beautiful invariance under changing t to f of t. This one does not. Notice that here, because there's no square root, if I change t to f of t, here I change, I get a square, and here I get only 1, so now it's not invariant anymore.
So you got a gauge freedom in that you don't have in this one.
Now you don't have gauge freedom because you fixed that freedom.
Okay.
And you fix that freedom, and that's why you have this extra constraint that sets the velocity to 1.
Okay, right. Thank you.
How many gauge freedoms do we have?
How many gauge freedoms
Yes.
do we have?
How many constraints can we apply?
So here we only have one gauge freedom, which was the freedom of changing t to f of t.
Uh-huh.
That's it.
Ah, only one, okay. Thank you.
I have another question related to coordinates.
2 orbits?
Coordinates.
Coordinates. Mhm.
We wrote a bunch of coordinates for the sphere.
Yes.
How can we tell if something is a sphere or not? just by giving the metric? I know there are some invariants, as you said, like the reach is scalar
Right.
and so on, but
So
do
one,
they tell?
yeah, good. Yeah. So one thing you have to describe is to always try to describe things that don't refer to coordinates and that refer to physical things. So you would like to say that if I am at the point and I throw two geodesics, for example, that the geodesics go away and they come back and they join. That's physical. That will happen in any coordinate system. For example, in the sphere that we have, we throw one like this and another like this, right? And they come and they meet together at the North Pole, and then they go around and they meet, and they come back and they always meet back and so on. In the other coordinates, it would look different. If I have this u coordinates, I would start from 0, and I would send one geodesic, and then send another geodesic. And they are straight lines in this u-plane, but then they go to infinity. And infinity is the same point, right? You have to be careful that infinity is the same point. That was why the metric has this big factor here that says distances at infinity are actually going to 0. And so those lines in the plane that were going like this, and then meeting at the end, they are actually the same. So how do we see that they are the same? We could say, let me go along one geodesic, measure the proper length, then go along the other geodesic, measure the proper length. When both are at proper length 1, measure the minimal length between them. All these statements that I just made are coordinate independent, right? You just say throw geodesics, keep track of the time that they measure, keep measuring lengths between the points at that time, and those experiences, those plots would be all the same, doesn't matter the coordinate, right? If I am in one proper unit of time here, I'm here. I'm in one proper unit of time here, I'm here. Then I measure the distance, I get this. I repeat the computation, I'll be here, I'll measure this distance, I'll get the same thing. And I plot the function of, as my proper length changes, how does my distance vary? And it's the same plot, the same physics. In this case of the sphere, there are other things I could compute, curvatures. I could check that the curvature is the same, that the point doesn't matter. Here, things look like they change. The origin and infinity, there is this rescaling factor. But if you compute carefully the curvatures, you will see the curvature is the same in all space. And there is curvature even though it looks flat. And this factor precisely gives it curvature and gives it a constant curvature. Now, computing curvatures, sometimes it's not enough. Imagine the curvature was not a constant, but it depended on the coordinates. And here it also depends. And then you would have to check that the map is such that it's really the same space-time. But for our purpose, I would say it's all about geodesics. So you should just imagine, for example, when we will have time, we can throw light rays, right? Then you just describe, I am a spaceship, I throw light rays, I receive light rays, and you describe your experience. And that description of your experience doesn't use coordinates. You just see, when my clock ticked midnight, I threw a light ray. Then I received it at 1 a.m. That has no coordinates there. So once you translate things to physics, there are no coordinates anymore, and then the coordinates are just a trick.
Hi, I have two questions. The first one, you were talking about being locally flat. Is that just an statement of that you can always go to the tangent space, or is there another stronger condition? And is conformally flat a stronger condition than having local flatness?
That's right. So local flatness is always true. That's just the equivalence principle. Just that if your space is smooth, you look very close, it looks flat, right? Like any curve looks like a straight line if I zoom in, right? Any surface looks like a plane if I zoom in. So that's always true. The statement that spaces are conformally flat, globally, that's a much stronger condition. Not all spaces are conformally to each other.
Okay. And also, when you say that conformal theory relates to local theories, is that a statement that works in both directions?
Can you repeat?
That the conformal theory relates to a local theory, as you can scale individually. in each point.
So I'm
That-
saying there exist theories. So in physics, there exist so-called conformal field theories. And these conformal field theories, these you can think of them, they are theories without scale. There is no typical distance scale. Okay? And that happens, for example, there's no typical length scale. All lengths are important. In those theories, it's often the case, although it's not proven mathematically, but we believe it's always the case, typically, that once you have this invariance under shifting scale, because there's no scale, that you can do it locally. It didn't need to be like that. It could be that there was a symmetry of the universe that you could rescale everything if you do everything, everywhere, the same rescaling. But it's not so surprising. You say, if the theory was scale invariant, maybe in some galaxy you could zoom out, in some other galaxy you could zoom in. That's maybe a little bit more natural. And indeed, we don't have any example of a theory which has this symmetry under scale that is global but not local. Whenever we found a theory that things are invariant and there is no scale globally, there's also no scale locally. Okay? But people that are more mathematical try to ask, is this a theorem? Can I prove this? That if a theory has no scale, that this symmetry, which was zooming in, zooming out everywhere, can be promoted to a much bigger symmetry, where now I can zoom in and zoom out, not only everywhere, but locally. Of course, the second one implies the first one, but it's much stronger. Probably it's true. It can be shown to be true in 2 dimensions. In higher dimensions, it's an open problem, but most people believe it's true.
I have another question from the gauge invariance of that Lagrangian. Does it give rise to another current or something conserved? That symmetry?
It's not a symmetry, it's a redundancy. It's a parametrization invariance. It's the statement that you can parameterize things in different ways and you are describing the same thing.
But is there any symmetry of this Lagrangian that gives rise to a current or something like that?
There are many symmetries of this Lagrangian. For example, this Lagrangian doesn't depend on t explicitly. It only depends on positions and velocities. So the energy, for example, would be conserved. If this metric is rotation invariant, for example, you could rotate this index zi and it would be invariant, and this would give rise to rotation symmetries and so on. We will explore this in the next lecture.
Okay, so if there are no more questions, let's thank Pedro. And we'll be back here at